Okay, the meetup starts in May 2013. At that time, I was doing a lot of volunteer. I was teaching R, Python, Hadoop, and in about half a year, I got paid client. That's how I started school. So right now, we're doing full-time program to teach data scientists and place them into different jobs. We mainly train people who have advanced degree, master or PhD in STEM major. So if you're a PhD of physics, PhD of math, PhD of EE, we're very interested in you. And we can place you into very well paid job. So we also have a lot of part-time program. If you're working professional, want to learn more and advance your skill, it's a great place to get started. If you're hiring, talk to me. If you're looking for a job, talk to me. We have a lot of things we can chat about. And this meetup is our main way to contribute back to the community. So if you have some skill you want to share with the community, please come and teach other people. So our meetup is very different in the sense we're not just showing you how awesome all the speakers are. We also try to make it like a workshop. That's why we always offer the source code, always offer the slides, and direct contact with the speaker. So let's see after the session how many of you will be able to do the same thing like tonight's speakers. And it's my great pleasure to present Xavier, Fangzhou, and the team who graduated from Bootcamp 2 about a month ago, and they officially on the job market. Xavier got Master of Corporate Finance and was a quant on Wall Street, and he's turning into a data science now. Fangzhou gonna get Master of Information System from NYU in about 2 months, so she's looking for a great opportunity too. And we have a few students from Bootcamp 3. They're gonna be ready before Christmas. So grab them in the end of November. And you got Master of Math, right? Didn't finish your PhD of Math.
Right, I just got Master's.
Okay, good. Okay, great. So how many of you have experience with Python? Spark. Good. Remember their name. Ask questions. How about R? Love Shiny? Great. Oh, another thing I want to mention is I put a lot of effort to make sure every meetup is reproducible. So we do desktop recording. If you go to here, you can click students' work. All the students will share their source code, no matter like they did several Kaggle competition. Most of them are ranked between 5% to 7%, and you can see their full solution. And the meetup part, we also did really good job to archive the content. So like when I teach Shiny step by step, when data IQ people come to teach how you analyze Medicare open data set, everything is recorded. So if even you missed the event, you can still go back to download the source code and follow along the video. Okay, so it's great resources. Okay, any question before we get started? Okay, we have free beer in the back. Make sure you grab some and don't get drunk. Wow. Okay, Xavier, your turn. Okay. Please welcome him.
Hi. Hi, so my name is Xavier Capdepon, and tonight I'm going to present you a project that I did during the bootcamp, and where I'm trying to determine the most popular R packages using Spark, Python, and actually R. So this is a little biography about myself, just after Vivian mentioned some of the points. So originally, I am an engineer specialized in hydraulic, and I have a master in corporate finance. More recently, I passed the first 2 exams to become an actuary, and I decided beginning of this year to actually take the full-time bootcamp in data science. And so we started in June. It ended a few weeks ago, and we learned R, Python, machine learning, and Spark. So to answer the questions that I'm getting during interviews, no, I didn't know anything about Python and Spark 4 months ago. The first link is the link to the different blogs that I wrote about the different projects that I made during the bootcamp. You have my email and my LinkedIn, and as mentioned at the bottom, I'm looking for a job. So please contact me if you have any opportunity. So the project guideline were the following. We had initially 7 days. It took me more than 13 days, including, since I'm using a PC and not a Mac, it took me more than one and a half day to actually install Spark. So I'm going to give you some of the link to actually try to figure out how to use the Spark on PC. For any user of Mac, it should be straightforward. So in this GitHub, I actually posted all the code. So the most popular R packages and dependency, which is actually a Python file, you have absolutely everything that I wrote from the beginning to the end. The structure of this file follows the slide that I'm going to show you tonight. The server script and output contain all the scripts that I wrote, which are contained in this main file, and all the data which have been generated by the server and by my computer. And in order to actually visualize, to have some visualization of the R packages, I put all the visualization so you can have access to the data in this folder called visualization data with R. And my presentation is also available here, the PDF. So the Python file look like that. So I put some of the links that you could need, some of the commands that I used to run the server, and after that you have my code, which is really long. And you will recognize some of the charts that I put in the presentation. So let me go back to the presentation. So here are the links that you may need if you have a PC to actually install Spark. It gives you step by step what you need to do and what you need not to do. This sparkapache.org link is actually the best help online you can find about Spark. And underneath, I will try to talk about it, but Spark is relatively simple to actually use once you installed it. So the first 2 lines that you need to write to actually call Spark into IPython are from PySpark import Spark context, and then you create a Spark context object. And so this mentioned here 7. I'm going to come back it later, but it actually means that you are using 7 CPUs, 7 core locally. So the project started with this website. So this is a website which was shown to us back in June by one of our teachers. And if you go to the link and read the article, you will see that the author is actually calculating, actually use the data available on the CRAN website, which is the CRAN website contains all the R packages and allow users to actually load R packages, and they actually track the download every day. So if you go on this website and you download these logs, you should be able to reproduce this graph. Unfortunately, she actually calculated the number of downloads every single day, and this author actually made a small mistake by actually stating that the R packages which are the most downloaded are the most popular. If you use R, you will know that every time that you try to download a package like ZooImage, R will actually look at all the packages which are already on the computer and download a lot of other packages that depends on which ZooImage is depending on. So if you actually calculate the number of downloads for each, it doesn't give you the most popular. In this particular case, the only one which was intended was ZooImage. All the other ones are consequences of the download of ZooImage. So here is the website containing all the daily log, containing all the packages which have been downloaded during the day. And this is all the what the log look like. So the interesting information here is the packages and the user IP. So you can see here that, for example, the user 1 during the day of October 3rd, 2012, downloaded 3 packages. User number 2 downloaded only 1, and user 3 downloaded this list here. So the methodology that I'm proposing to use to actually try to calculate the most popular R packages is for each user to look at the list of packages which have been downloaded during a period of 24 hours. If I'm able to actually find the information regarding the dependency of each package, I will be able to determine what packages were intended. We are going to call them root, and then if I'm able to find all the packages for every single user, I will be able to count them and determine which one are the most popular. So how do we do that? There is so the CRAN website actually contains the list of all the packages, and there is more than 7,000. So, but this number is changing every day. The day I did it, the CRAN website was containing 755 packages, and for each of them, you have. So, for example, for ggplot2, which is one of the most used packages in R, you have 2 lines, depends on import, that contain all the packages that are downloaded as a consequence of ggplot2. And this big list here contains all the packages that actually depend on ggplot2. So I'm going to scrap all this information using Spark and Python, and I'm going to talk about it later, but it appears that the information contained in these 2 lines on the entire on the entire panel of packages should match all the information here. So this is why the depend matrix is equal to the transpose of the reverse depend matrix. Is there any question at this point? So the script has been built in 3 steps. First, I'm going to build, and I'm going to show you how to build a matrix of dependency. Then there will be a part of how to download all the logs, which is relatively easy using Spark. And the third step is to actually process all the information contained in the logs to try to extract the root packages. So just to give you some numbers associated with this project, there is 7,055 packages to scrap. So one single core cannot do it. Since there is 7,055 packages, my dependency matrix will contain more than 49 million elements. And then the log, so I'm doing the study between January 2015 and end of May 2015 to be on the same period than the article. And all these packages, all these logs contain approximately 300,000 lines. So which means that at the end, I will have to process more than 45 million line items. So the first step that the first thing that I did is actually to list, just using Python and Beautiful Soup, to scrap the list of all the packages. The second step is to actually build a dictionary of index versus the name of the package and the reverse index versus name. The reason is to actually reduce the memory that I'm going to use during the process, and also to reduce the size of the different files that are going to be generated during all this process. And then for each package, for each web page describing the package, I'm going to use a web scraping and some regular expression to grab the information regarding the dependency and the reverse dependency. And then, as a fourth step, I can actually build the dependency matrix. So just to take the example that I showed at the beginning, package A doesn't depend on any package, so it's going to be a line of zeros. B depends on C, D, E, and G, so I'm going to have 1 in the column C, D, E, and G. Is that clear? So I believed that my matrix will be 7,000 by 7,000. Actually, there is a trick. We can use a sparse matrix, which is a concept that I never heard about before, because in my math class, and it's actually a concept which is used in computer science, but not in math. The reason being, we can build a matrix with plenty. If the matrix contains a lot of zeros, which is a suspicion here, we can use this concept of sparse matrix because it's going to reduce the size and the time to generate it. So what we need to do is to actually generate every single index, every single element coordinate. So with my example that I had before, package B depends on C, D, E, and G. So the index for B is 1, because in Python the index starts at 0. So it's going to be 4, 1, and C, D, E, and G will be 2, 3, 4, and 6. Everybody follows? And the data is going to be for every single element in this particular case, every single element of the matrix is either going to be 0 or 1. So we only care about the 1. For those who are already familiar with network visualization, it appears that the row and the columns here are the source and the target for the node visualization. I realized that a few weeks ago. So Python contains several really useful functions associated with sparse matrix, including the CO matrix, which actually allows you to regenerate the entire 49 million items matrix and get rid of all the duplicates, and also allows you to re-extract easily in different formats the sparse matrices elements. So here is a simplification of Python versus Python plus Spark. So if you have a list of elements in Python, you will do a loop, and you will get a result. In Spark, the idea is to parallelize the task to get to the same result. So what you need to do, what Spark is doing is actually sending the task, splitting the list in different objects, sending it to different core or to different computers, and manage to reunite all the results in one single list. So by using the two lines that I showed before, you just need to RDD your list by using this SC parallelized, and then the list is mapped, which is the concept of map reduce in parallel computing, collect, and you will get your results. So it's a little bit of a simplification, but I did not, for this particular project, I did not use any EV function in Spark, and it's, once you know Python, it's relatively easy to, yes?
Did you use Spark or PySpark?
PySpark.
SQL context.
Sorry? Sorry?
Instead of SQL context, it could be SQL context SQL.
Yes. I'm not sure to understand your command.
Spark context.
Yes.
Called PySpark. There is a subclass called Spark context SQL.
Okay.
Using that.
No. No.
When using Spark, so a lot of people talk about Scala because my understanding is that's how it's developed in, and that's where a lot of people use it. And do you know whether there's any practical difference in accessing it in Python versus Scala?
No, unfortunately, no. I'm too new in Spark to be able to answer that question. So the results are the following. My depends matrix generate 14,000 elements. The reverse dependency generated a little bit more, which means that the website contains some inaccuracy. And by combining both, just by taking the transpose of the reverse dependency should be equal to the dependency. So I just aggregate these two results. And by using the CO matrix that I described before, you get to a final number of 435 elements, which means that there is on this 49 million element matrix, you have only 14,000 which are different from 0. So just on the so the school has an access to one of the server, that we call the 82. It took about 40 minutes to generate these two matrices. I calculated this is an approximation, but it will have taken me more than 8 hours on my own computer to do the same thing. The reason being is that you need to constantly scrap the CRAN website, so you need to launch several requests at the same time, and this is what takes time and memory. Yes, sir?
Does that include the web scraping, or that's just in-core, in-memory processing?
That's the 40 minutes includes sending the request in web scraping, getting the data,
Okay.
cleaning it, and generate all the elements of the matrix.
Do you have a breakdown of how much of that was
No.
just IO
No.
versus
No.
in-memory? Okay, thank
No. I think, by experience, I think the web scraping is taking most of the time, just by sending the request and loading it. So yes, one other point is I've been trying to do the work during the day. I'm getting a lot of errors, even if the code is actually right. So it appears that after 10 p.m., it's much easier to actually get everything, to get the full matrix to be calculated. There is my understanding is that a lot of people are actually loading packages during the morning, and in the afternoon, the CRAN website is actually maintained, so it's much easier at night to do the scrapping. So the findings are the following: the most the package which are the most greediest, which are really greedy in terms of using other packages, are this VMS base, which is related to fish. So this is to count fish. The second one is a package related to genetic data, and it's actually consuming at least 23 other packages. The third one is also related to microbial ecology, and it's consuming 23 packages. In terms of most reversed, meaning the package which are supporting other packages, the mass package, which is a modern applied statistic with S, is connected to 679 other packages. RCPP, which is actually a C++ integration, to 400, and ggplot2 to 351. And then on Friday, I spent one day to try to get the correct code to try to find the longest path between our packages. I'm going to talk about this result a little bit later. But you will see this is the reason why my project is still going on. So let's look at the visualization. So this is generated with R. And R is generating a D3 JavaScript. So this is why this is interactive. So here, what is interesting is you can recognize ggplot, and the big one here is mass. So just to show you the code behind it. So the Python script is actually generating all the input. This is not what I wanted to show you. So this one is actually I can actually. So let's look at the data. So here, this is a small list, so let me show you something else. Let's look at this one, links. Links, this is actually what I was telling you earlier with the source and the target. It provides the links between one package to another, and the dependency to another one. So this is actually the what we call the sparse matrix. And here you have the 10 package on which other packages are depending. So in pink, here you have, in pink here, ggplot is actually depending on 7 other packages to run, among which mass and plier. And plier is actually using RCPP to be able to run. This is what this visualization is showing you. So this is the 3 most greediest packages. So you will recognize the genetic package, the package related to microbiology and VMS base. This is the 10 most greediest packages. Well, there is a vague error, but you see the you see the visualization. And this is the 100 most greediest packages. As you can see, at this point, there is nothing to actually see. But you have the mass package here. I guess we can find RCPP. So visualization is supposed to show. This show you that all the packages are interconnected.
Okay. But you don't need this visualization to tell you.
Yes. But what I wanted to show you is that I could actually use the sparse matrix in R to show you the network of packages and the interaction between from one package to another. Yes?
What is the name of the package that produces this?
Network D3. Yes. So, and this is the longest path between. So what this graph shows you is that there is 11 degrees of dependency between this package and the basic package in blue. 1, 2, 3, 4. So if you look at the path, there is 14 combination. Is that clear? Any question? So the second part is to actually download all the logs containing all the information regarding the package and the user ID. So the code is relatively simple. I generated, before using this script on the server, I generated a file called URL log full path, and I'm loading it. I'm making a list of it, and then I'm parallelizing the list. I'm using the function download, which have been defined here, and I collect, and immediately all the files are saved on the drive. So the third part is to actually try to download, to actually process these 150 logs. So I talked to Sam, who was our Hadoop teacher, and he told me that I had two choices. Either I was processing every single file that I downloaded immediately with Spark to get the result, and Spark will aggregate all the results together. There was another solution, which was to actually aggregate all the 150 logs into one single file, which could have been a NoSQL file, and then RDD this entire file and reapply a task to get the result, to get to the result. So I choose the first solution because I was more comfortable with the first solution, and since I was actually I would have to have processed every single file to put it in one file. I felt more comfortable to actually apply immediately the task on every single file to get to the result. So the result is the following. Between January and May 2015, there was 47 million line items to process. Overnight, I run the script on the server with 10 CPU several times overnight, and it took between 5 and 9 hours. And from this 46 million item, I'm getting 18 million routes, meaning 30 million of download were actually a consequence of, was just a consequence of trying to download one particular R package. So here is the graph that we can obtain with this information. So this graph shows you the download per day for the period between January and May 2015. So the average daily download is approximately 300,000. The lower point corresponds to the weekend. The highest point usually corresponds to the business day. Is also we can also notice that in 2015 there is 300,000 downloads a day. In 2012 it was only 100 because R became more and more popular. This second finding is about one of our teachers who actually built one of the packages which is in this list of 7,000 packages. And this package, Crack, has been downloaded 1,400 times. And given my methodology, it's ranking 1,170. And finally, by analyzing all the data that I processed, this is the new graph that I'm getting. So the most popular R package would be RCCP Eigen. And you have the list of the 20th most popular given my methodology. So to be honest, I am a little bit skeptical about the result because I was not expecting packages like Mass, RCCP, and Matrix to be in the top 20 most popular packages. So there is several reasons that can explain this result. The first one is that I actually use the first degree of dependency in my matrix. I did not build the entire matrix of dependency. But now that on Friday I managed to calculate the longest path between packages, I can now put an upper limit on the iteration to generate this n degree dependency matrix and be able to try to regenerate the result. There is two other things that I also need to mention is that, and it bothered me, because it's actually giving us a small error in the result, is the fact that our user can be in a foreign country. If he actually download our packages overnight, he's going to get two different IP, and I'm not able to recognize him. So there's going to be a small error on the result. And the last point is that all the old packages are not referenced anymore in the CRAN website. So I need to take them into account, but I don't have any information regarding dependency about them. And finally, yes, the testing on this particular project was extremely time-consuming. The reason being is that I was telling you before, the CRAN website is constantly updating the packages. So the count of packages can change by more than 20 every day, because they delete all packages and put new ones. And also because the result is going to change from one day to another, because the author of the different projects have tendency to actually increase the functionality of their package by increasing the dependency of their package. Here I am. Any question? Yes?
I noticed in your Python, in your small Python program, you used a lot of list comprehension.
Yes.
Is that a best practice, or does it make it slower? Does it speed it up? That's one question. And the other one, the package that had the most dependencies, that crazy big one, what did that one do?
The mass?
The big one that had all
Yes, the mass is actually,
that was mass? I mean,
yes, mass. This is actually to do the transition between S and R, yeah.
And the list comprehension, is that like best practice for
This is my way of writing lists in really short way. Sometimes it's not shorter, but most of the time it's shorter. But it's also to actually try to compress the number of lines that I'm writing.
I think it might be slower if you do.
Too many?
People think depending on list comprehension, it might be slower, so you might
Okay.
speed it up to break it up.
Okay.
It's the same as recursion. Oh, so it's heavy on memory, I guess.
As opposed to using list comprehension, use what?
Iteration. You're saying list comprehension.
What does everybody else think? List comprehension?
Python, list comprehensions are pretty fast.
Yeah.
And pretty memory. They're not memory logs generally. But that's pure Python, right?
I've never had any problems with this comprehension.
Yeah, the more I read this comprehension.
I've heard people say that they're faster, so.
Oh, okay.
But I would say just try it out in time.
I've heard other ones. I've heard this comprehension is bad.
Let's not fight.
Any other question?
I think this is great. Are you going to publish your results to the people who administer CRAN? Maybe we can speed up certain packages. You think this might bear some results or some fruit?
I'm just worried for the package which have the package like the package which have 12 degrees of dependency. Yes, if one package doesn't work, all the chain doesn't work. So But my guess, given the fact that they actually disclose the dependency for every package, I'm wondering if they don't already know that.
Which server did you get these logs from? Because other people did this similar study, maybe not as elaborate.
This
But they refer to
this website here, cronlogs, rstudio.com. Yeah. Yes.
So this is the RStudio.
This is RStudio logs. Yes.
It's their mirror.
Yes.
Okay. But there are other logs.
There's another log from the competitor of RStudio. Yes. But I'm not sure that they actually disclose anything.
Okay.
This is the original one.
RStudio is probably the most comprehensive one.
Yes.
And then CRAN itself doesn't publish download logs.
Any other comment? Or do you have another question? I don't know. I need to check with the boss first.
I have one more question. These 7 boxes, were they local to where you lived or to where you worked, or were they like a digital ocean thing that you spun off?
Sorry,
I'm sorry. Were these cloud boxes or boxes that you had at your office? The 7 environments that you used for the Spark.
No, actually, there was two things. For Spark, I had Spark installed on my machine to actually be able to test all the scripts. And the school was actually letting us use a server where Spark was already installed. On this particular server, as far as I understand, because I never got the confirmation, I understand that it was a server with 12 CPU, 12 cores, and there was a lot of memory, but I don't know how much. But it was much more powerful than my machine.
More reliant on how good it's connected to the internet, though, is.
So this particular server during the day was really bad with connection. So I don't know if this is the connection between my computer and the server which was bad, but I don't think so. I just think that the CRAN website was actually shutting down the entire thing.
Yeah, that may have been limiting.
Yes. Yes.
Any reason why you use 7 cores? You try using a different number?
Yes, I use. At first, I used 7 because this is a number we had in one of the slides. And for the first part, I used 7. For the second part, because it was taking so much time, I used 11.
It depends on your machine and how you're going to split into virtual machine.
Okay.
One last question. We have another huge project to present to you. One last one.
So when you, as you're going over the internet, couldn't you just download it in one mass into your HDFS or something, and then like query it from the client or?
The script was pinging the internet on
Yes.
every run.
Yes.
Run that a little more efficiently.
Yes, but how do you, since every single package is one web page, how do you ping the website without pinging the actual address? You need to actually unique. Sorry? So the thing is, in this script, I'm only pinging and downloading the information once. I'm only launching a web scrap against one web page once. The thing is, I need to do the 7,000 at least once.
We taught how to parallelly scrape website before. Did you use any parallels?
Yes, I'm using Spark to do that, yeah.